Before we introduce Newton's laws of motion, we want to define a quantity known as momentum. All right, so we talk about the linear momentum. So we talk about the momentum of a body which is traveling in a straight line. The linear momentum of a body is defined as the product of its mass and velocity. So therefore, momentum equals mass times velocity. Writing that in symbol form, the symbol that we use for momentum is a small letter p, so you'll need to get used to that. Little p equals mv. The SI units, mass measured in kilograms, velocity measured in meters per second, and we leave it like that. You might remember in our stuff on units, in some cases we change the units in these base units for force, for example, and call it a Newton. In this case here, we don't come up with a special name. We just leave the units as kilogram time meters per second. So here's our mass. Our mass, little m, moving with velocity v. And there's one other thing we should just note about momentum as to whether or not it's a vector or whether it's a scalar. What do you think? The diagram on the right here shows the thing moving in a particular direction. So we need to note that momentum is a vector quantity. And earlier in the year, we looked at vector subtraction in terms of working out change in velocity. This is another place where we will use vector subtraction a bit further through this topic in terms of change of momentum. Right, Newton's first law of motion. A body stays at rest or continues to move at constant velocity unless a resultant force acts on that body. All right, resultant. Take note of that. Right, so a couple of little examples here. Let's say we've just in this left-hand diagram got a box sitting on a horizontal surface. Then there is going to be a weight force downwards, the force due to gravity, and there will be an equal and opposite upwards force. You could call it the reaction force. That sometimes can be a little bit misleading. So I'm going to call it the normal force. The word normal here meaning that it's acting perpendicular to the surface that the block or the box is sitting on. And so those two forces, let's call that one N for short and call this one W for short. We can say that W equals N. The sum of the forces acting is 0. There is no resultant force. If we look at this next example, we've got a triangular shaped block sitting on a sloped surface here. So once again, we've got the weight. Once again, we would have a force normal to the surface. And there will be a third force acting, and that's going to be a force of friction acting this way, which would stop the thing moving down the slope. If we were to add those three forces together as vectors, we would again find that the sum of the forces acting is 0. There is no resultant force, and therefore there is no motion. This is on the basis that this triangular block is sitting on the surface and is not sliding. If it was to start to slide, if we increase the angle of the slope, we'd get to a point where the component of the weight force overcomes any friction effect, and then there would be a resultant force acting. All right, an old Lotus, I think it is, Formula One car here. Let's not consider the vertical forces. Again, we would get like a reaction force here and a reaction force there, a normal force at those two places, and a weight force. And we know that those forces are going to be equal and opposite then in terms of the motion. But we're going to have an engine force, if you like, forwards, And we're going to have a whole pile of friction forces, air resistance, friction in the engine, friction in the bearings, etc. backwards. If that vehicle is either stopped or if it's moving at constant velocity, then again we could say that the sum of the forces is 0, or that the force of the engine is going to be equal and opposite to all of those forces of friction. If we want the car to accelerate, then we have to make the engine force bigger so that there is a resultant forward force and we get acceleration. If we want the car to decelerate, then we have to make well, we've got two choices. One is we could make the engine force smaller, sorry, wrong thing. Make the engine force smaller by taking our foot off the accelerator, and now the friction forces are larger and the car slows down. Or alternatively to doing that, we make the friction force much, much bigger. Done it again. Make the friction force much, much bigger by putting our foot on the brakes. Okay. Newton's second law of motion, the rate of change of momentum. So at year 11 level, you talked about acceleration. We're changing the way we define things here. The rate of change of momentum of a body is proportional to the resultant force applied let's just tidy that business up there. And the second part of the law that people often forget is that we say that the change of momentum is proportional to the force applied, the resultant force applied, underline the word resultant there, and takes place in the direction of the force. So acceleration or change in momentum is always going to be in the same direction as the force that is causing that to happen. All right, so taking that Newton's second law and starting to turn it into an equation, change of momentum over time taken would be rate of change of momentum. And we're saying that that is proportional to, that Greek letter alpha means is proportional to the force acting. So change in momentum, P final minus P initial, well, that looks a bit like vector subtraction to me, if we had different directions involved, divided by time taken, proportional to F. Momentum, mass times final velocity for final momentum, minus mass times initial velocity for initial momentum, proportional to force. Let's take the mass out the front of that statement on the left-hand side. V minus U over T, proportional to F, mass times acceleration, proportional to F. Acceleration equal V minus U over T. And so we get something that's starting to look like our formula F equals ma. And the only thing I'd say is that if we want to turn this into an equation, all we have to do is choose the appropriate SI units for force and mass and acceleration, and then we can put an equal sign into that instead of a statement of proportionality. So there's our familiar F equals ma, but it's based upon an initial statement that talks about rate of change of momentum. And of course, the units of force are going to be newtons, as we already know. All right, now related to that Newton's second law of motion is our definition of force. So if you are asked to define what a force is, you do not say that it's a push or a pull or something like that. What you do say is that force is defined as rate of change of momentum. I want you to lock that away. We're now working at AS level. We're now working at year 12 level, and so our definitions become more sophisticated than what they previously were. All right, here's a worked example, similar to one of the problems that you'll find in the worksheets. An aircraft of total mass 30,000 kg needs 1,000 meters of runway to reach its takeoff velocity. The takeoff and landing speeds or velocities are 50 meters per second. Find the acceleration needed to reach this takeoff velocity in 1,000 meters. So this first part, again, is an equations of motion problem. So initial velocity 0, final velocity is going to have to be 50 meters per second. The distance that we travel, or the displacement, is going to have to be 1,000 meters, and we are trying to find the acceleration. Identify the equation. No time in this one, so it's v squared equals u squared plus 2as. All right, 50 squared equals 0 squared plus 2 times, the a is what we're trying to find, times 1,000. 50 squared, 25 with 2 noughts on the end, equals 2,000 a. A is going to equal 2,500 divided by 2, or 2.5. Sorry, 2,500 divided by 2,000, which is 2.5 divided by 2, 1.25 meters per second squared. All right, what resultant force is needed to reduce the acceleration? So in terms of resultant force, it's simply going to be F equals ma. Remember that in this formula, that is the resultant force. Now, I think we might just go back a couple of slides to where we got our F equals ma formula and note that down, okay? Here. I think it's worth highlighting that that is resultant force, and you really got to get that locked into your head, that that's what that force is referring to. All right, so resultant force, F equals ma, and so it's simply going to be the mass of the aircraft, which we said was 30,000, times 1.1, or was it 1.25, wasn't it? Sorry. And what's that going to equal? It's always good to do these things in your head. A quarter of 30,000, well, a half of 30,000 is 15,000, so a quarter is 7,500. So 37,500 newtons needed to produce the acceleration. All right. Final part of the question. I'll just remember that 37,500 newtons as being the resultant force. If you've got your aircraft traveling forwards, okay, on the runway, if we put some wheels on it then, where are the wheels going to go there, let's say, okay, we need a resultant force of 37,500 newtons. That's what we've got to get overall, but what we're being told is that there is a force opposing the motion of total of 12,000 newtons. So therefore, the actual force applied is going to have to be 37,500 plus 12,000, 49,500 newtons. That's the actual force that the engines have to apply, what's called the thrust, such that when you remove the friction forces over here, you're still left with the 37,500 newtons that's needed to produce the acceleration. Final slides here. Different version of the laws of motion. Bart's first law, a body at rest remains at rest until a parental body comes over and tells it to mow the lawn. If that body continues to remain at rest despite the urgings of the parental body, then you need to see Bart's second law of motion, which states what's going to happen. In the second law, the acceleration produced by an unbalanced force acting on a body is directly proportional to the mass of the body, mass of the force, sounds a bit rubbishy, plus whether or not the force is carrying a weapon, plus how loud the force is screaming. And the third law, which I'm actually going to give you in a separate video in terms of the real law, but in terms of Bart's third law of motion, when a body exerts a force upon another body, the second body exerts an equal force upon the first body, and these forces are opposite in direction, i.e. for every action there is an equal and opposite reaction, which is not how we are going to quote the third law of motion, even though that I know this thing here is the traditional way that law is quoted.